In this part, we will look into various aspects that contribute to the latency that we experience while doing magnetic disk access. So before that, let's look at response time for disks. So response time is the total time that from the point where operating system issues a command to the disk and the point where the data is actually received by the operating system. Okay. So here, first we look at access time. So access time is, let's assume that the command is received by the disk controller. How much time does it take to transfer the data back to the operating system? So here, there are three components that contribute to access time. First is seek, the time it takes for the read or write head to seek to the correct sector where the data is. Okay? Then the second component is rotation. So here, once the head is seeked onto the correct track, we also need to rotate the disk or like rotate the platter so that the sector is correctly aligned. So there is rotational latency. And then finally, there is transfer delay, which is like once the data is read, we need to transfer the data to the operating system. So this is the access time. This is assuming that the command is received by the disk controller. However, in reality, commands may be queued. There could be many commands that are issued to the disk, and these commands could be queued so that the disk haven't even received a command yet. So in this case, so we also need to consider the queue time, the amount of time a request spends in the queue as well. So response time includes the total time that a request spends in a queue, and finally access time, which is once the command is received by the disk controller, how much time it takes to transfer the data back to the operating system. So first, let's look at seek delay or like seek latency. What are the things that contribute to the seek latency? So seek time or seek latency is the time required to move the head to the appropriate track where the target sector is, right? Or target block is. So note that seeking is physical. So we need to, it is a physical movement of the read head to the desired track. Okay? And this is not electronic, this is rather mechanical. Okay? And this has four components, right? First, the disk head needs to accelerate so that accelerate to move, and then it needs to coast at max velocity, and finally it needs to decelerate, and then it needs to settle onto the correct track. So there are four mechanical components that contribute to the seek time. And furthermore, seek time also depends on the workload. So if you have random seeks, then of course the seek time would be really high. However, if the data that we want to access is on like adjacent tracks, then the seek time will be low. Okay. And similarly, there is also rotational latency. So this is the delay. This is the time it takes for the disk to rotate so that the sector that we want to read is correctly aligned with the read or write head. So here, the rotational latency depends on the rotation speed. So here, the rotation speed of disks is usually measured in rotations per minute, RPM. So how to compute average rotational latency? So assuming random access, assuming that the data that we want to access has equal probability of belonging to one of the sectors, okay? And here we have like each, depending on the sector, the delay would be more, right? Like if the sector is the last sector, then the delay is one rotation. However, if the sector is one before that, the delay would be slightly less. So given that the probability of data being at each one of the sectors is same, and the delay is proportional to the distance from the current head to the target sector, the average rotational latency would be half revolution. Okay, so average rotation latency for any axis would be half revolution. So now given this and given the RPM of the disk, we can calculate the rotational delay as the amount of time it takes for full revolution, that is inverse of RPM, and then divide that by 2, that will give us the average rotational latency, which is half revolution time. So on modern disk, seek times are usually 0.5 to 15 milliseconds. On an average, it's 5 to 6 milliseconds, and it improves 7 to 10% every year because of the advances in manufacturing parts, advances in firmware. So this gradually is improving. It improves on an average 7 to 10% per year. Similarly, rotation speed is 5,600 to 15,000 RPMs, and it also improves at the similar rate. So disk fails more often than the tapes when continuously powered on. So especially when you connect disk to the power all the time, the chance of it failing is more. And it could also fail under heavy workload or heavy usage. And it could also fail because of high temperature, because the magnetic properties that are needed to store data on the disk might change with the temperature. And how do disk fail? Like, what are the symptoms of failed disk? So in worst case, the whole disk can just stop working. So this could be because the mechanical motor on the disk died, or there are some errors in the firmware that deals, like there are some errors in the disk controller itself. Or there could be some transient problems because of improper connection, or because the actuator is slightly off. So there could be some transient problems which could be fixed. Or there could be more fine-grained problems, like individual sectors on the platter might fail. Okay? Because of there could be a scratch, like if the disk is reading, if you try to move the disk, then because of the mechanical movement, the read head might get really close to the track, and it might scratch the surface of the sector, in which case the sector could be unusable. Okay, and the data that we have stored on the sector or the block could be inaccessible, could be lost forever. So, however, disk have some error recovery capability. So there are certain things that the disk controller itself does to recover from errors. One most common thing is error correcting codes. So these codes help us detect errors, and in few cases, these codes also help fix certain number of errors in the bits. So depending on the length of the error correcting code, the reliability or the correcting capability of the error correcting code improves. And in few cases, disk might itself try to read and write multiple times. When certain read fails, it can try to do some heuristics to see if it can fix a bad sector by trying to read at slightly different offset than the desired offset. And other most common thing that the disk controller does is to remap sectors. So if disk knows that there are certain sectors which are bad, okay, so it can avoid reading or writing to those sectors. And whenever a read or write comes to those sectors, it can actually remap to other sectors. Okay, so disk controller can take care of certain problems. However, if this control itself fails, then yeah, it's hard to recover. And the chance of disk failing is just relatively higher, or rather like very high than tapes, because tapes are mainly static components. There are no active components in the tape. Whereas in disk, there are a lot of moving parts, there are a lot of mechanical parts. So the chance of it failing is considerably higher. And that's why, like, if you ever used a disk, so there are actually external disk mounting racks where you can take a disk, magnetic disk from your PC and try to mount it onto this external disk. And if you have one such device, and when you connect it to a laptop or your desktop, and when you're reading it, you can actually, when you touch the disk, you can actually feel the rotation of the disk platter. Yeah. So if you try to move the disk, there is a high chance that you might actually uh, make the head scratch the surface of the disk platter and might corrupt certain sectors. Okay. So in the next part, we will look into flash memory and see how, like, what technology we use in flash memory and the advances in the, like, how we move the code that needs to deal with the uh, storage systems towards the memory itself. Thank you.